Okay, hello again. 5.8, inverse trig integrals. The last section with new integral formulas. 5.9, we're not doing. You don't need to do. That's nothing to do with, it's not required for this class. Another fun fact is that my teacher in high school made me do hyperbolic sine, cosine, tan stuff, and it was not a part of the AP curriculum back then. She wasted our time, and yet she skipped over the second fundamental theorem of calculus, which was very much a part of the AP exam. Anyways, I'm clearly only a little bit bitter still. Okay, so 5.8. This is, if you look at the notes, I think I even wrote this in the notes. This is actually, I think, when I said before that 5, 6, and 7 were my favorite sections. Just kidding. They just get better and better. 5.8, I think probably the end of 5.8. This is like the pinnacle of just like doing an integral. Like you see the integral, do the integral. Right after this, we're going to go and talk about differential equations. In the early part of chapter 6, and then we're going to talk about area between two curves and then three-dimensional volumes by revolution. And that'll be the new material, and then we'll L'Hopital's rule for a day. And that's all. But this is kind of the pinnacle of just the mechanics of doing an integral, and that's really exciting. Again, it's like the epitome of all these like puzzly critical thinking things. Okay, so 5.8 starts with inverse trig integrals. You'll notice in the box on page 363, you might be thinking, oh, look, there's only 3. Usually when we do trig stuff, there's 6. Right? You notice there's something involving arcsine, involving arctan, involving arcsecant. Your first question might be, well, where's arc cosecant, arc cotangent, arc cosecant? Well, if you remember back to, we took the derivatives of those things. They were just the negatives of their non-C, their non-co counterparts. Like the derivative of arc cosine was just the negative of the derivative of arc sine. Derivative of arc cotan was the negative of the derivative of arc tan, and so on. Well, now that we're going backwards, right, we need to know how to do the other one, because if we were given arc cotan, we couldn't really just like magically transform it into arc tan. Those things are pretty different. But here, when we're working backwards, if we're essentially given something that's just like the negative of something else, well, we can just write that final answer as the negative of the original thing. So essentially, we're just going to give all our answers in terms of arcsine or arctan or arcsecant, and if they happen to come out with a negative sign out front, so be it. You can just, kind of grin in the back of your mind, know, yes, that could have been an arc cosine problem, but we don't have to do that. Anyways, so there's only 3. Makes it a little bit easier. You do have to memorize these. Again, these are more or less just working backwards from what we had. A couple differences. So we have, and they do this in terms of U. I'll just, well, the problem is I don't like the way they do this here, because they have a U, but they also don't show that there's a U prime in the numerator, which would be required. So I don't know why they use a U and not a U prime. That's strange to me. So I'm not going to use U. I'm going to use X, because that seems more consistent. And you just know that always we're going to be on the lookout for having to undo chain rule, and the same kind of like fit the form type of thing or force the form of undoing chain rule is going to always apply. So I'm going to, and they write their du like in the numerator. You should be able to not be scared by that because sometimes the AP will write it like that. But I'm going to write this as like 1 over, like in this first one. This is how I'm more used to seeing it. Oh, there's a square. Here. That's a 2. Minus, and I'm going to do x instead of u's. Right? So I'm putting my dx out here. And this is the arc sine one. One thing you'll probably notice it's a little different. Oops. You'll probably notice it's a little different is that there used to be 1s here instead of a's. But now we're given a's instead of 1s because, well, it might be, and there might be a number there, right? So a is a constant. So a is a constant. A is a constant. Okay. This is arc sine. As I write this down, notice each of these. So arc sine is the only one hopefully you're looking in the book, but it's the only one that does not have a 1 over a out in front of it. It's just arc sine. And again, I'm writing it in terms of x instead of u. X over a plus c. Notice this is just like if you take out the a, right? Because we didn't really put an a in our formula before. If we take out the a, then, right, derivative arc sine x was 1 over square root 1 minus x squared. So that still is building on the knowledge that you already hopefully still have. All right, next one is arctan. Now I will say arctan, this is going to bother me. Arctan is used the most. It's used more than arcsine because it doesn't have a square root. It's more basic, especially this integral, right? Take the derivative of arctan, doesn't come up as much, but having the integral of something turn into an arctan is actually very common. Which I don't know, to me is kind of like surprising and interesting because like boom, you can just have like a normal looking function like out of nowhere. It's not just like a tan comes in, like inverse tan comes in like out of nowhere. Like how crazy is that? Like you're trying to find the like area under like a, I don't know, 1 over like x squared plus 4 curve or something. Then like boom, to find that area you need inverse tangent? What in the world? I don't know. It's kind of a cool fact in math for me. Okay, 1 over a. So notice this has this 1 over a outside. Arcsine did not. Arctan x over a plus c. Okay. And the third one is in arcsecant. And if you remember the weird thing about the arcsecant, so let me write this down first. X squared minus, and again, I'm so used to writing in a 1, it's kind of weird to write an a. These things have a's instead of 1s. This also has a 1 over a out front, arcsecant, secant of, and here's an absolute value. So if you remember, right, so this is something, oh, but that's not what I wanted to do. Yeah, let me undo that and let me do it on, on these things. Okay. those absolute values used to be when you were going, so like derivative arcsecant used to be on this thing here, right? The part outside the square root. But in this case, we're just assuming that you don't normally start out with an integral that already has a square root written in there. So we're wanting to force the domain of the output to match the domain of the input. Anyways, not a big deal. Just do it. So let's see. So we have the absolute values there. Hopefully you can remember that because you remember where the absolute values used to be in the derivative. Other things, let's see. Notice these have this, but this does not. There's not that in front of the arc sign. They all are divided by a. Now notice that's a, not a squared. Right, so these are all divided by a. And again, we're going to have the same problem as we did when we did derivatives of inverse trig before. Just so important, this is x squared, x squared, x squared. And this is a squared, right? A squared, a squared, a squared. When this is really important, right? Like if instead of seeing an x squared there, if you see something like, I don't know, 4x squared with no parentheses written there. What that really means is in the parentheses, you would have like parentheses 2x squared. If so, that means like your u would be 2x, which means you're looking for a u prime of 2 in the numerator, or you might have to force it, right? So that whatever your inside function is going to be here. That's where we're looking for it here, right? So this is going to be where your inside function goes. Same thing here. All right, stop it. Inside function goes here, or inside function goes, in this case, both here and here. So anytime you have something in here that's not just an x, you're going to have to do the derivative of that thing, have that present in the numerator, right? So again, you would need if it's not an x inside these green boxes that I drew, you're going to need the derivative of that u in the numerators, right? So if not just an x inside these green boxes, you need, right, u prime or du dx in the numerator here. Okay, just like with chain rule, that's always implied. You always have to undo chain rule if there's a chain rule there to undo. Just like with derivatives, you always have to use chain rule if there's any kind of chain rule there to implement. Okay. Now this example 1, there's not much writing, and again, to save time, I'm not going to write down all this. But I hope you can look at this with me. You could write it into your notes as we talk through it on page 363, the bottom example 1. So notice for A, the 4, right? So you should first of all notice that the integrand seems to fit the arc sign kind of form. And notice it's 4 minus x squared, but the 4 represents a squared. So what's being squared there? A 2. So what is your a? Your a is 2. Your a is not 4. Right? So notice then when we go to apply the x squared is just x squared. So no funny business. You don't need like an extra u prime in the numerator. It is what it is. Right? And your a is different than anything having to do with like an inside function u thing, right? And a just goes along for the ride as part of the formula. So if your a is 2, right, you just write down your arc sine with an a value of 2 so that it's arc sine of x over 2. 2 is your a value plus c. That's it. Example 1, part B. This one's trickier. Again, I could write this down, but I would write down exactly what the book's writing. So you look at part B. Again, notice this is why arctan is so much more popular than the other two, because you don't need a square root in the denominator. It's unsuspecting. You look at that, it doesn't even look that strange. In fact, you'll see what's going to happen later. Even stranger things are going to happen. Haha, like the TV show. So 2 plus 9x squared. So that is actually an arctan problem. Hopefully obviously, right, for arctan, it doesn't have to be the constant squared plus the variable part squared. It doesn't have to be that order. Obviously, you could have the variable part squared plus the constant squared, right, commutative property of addition. But notice here, you should first rewrite this to fit the form so that it looks like an arctan problem, and also then to identify your inside function and what your u is. Again, I could write this out, but I mean, I really have nothing else to write other than what they're writing down. So the 2 has to represent a squared. So what's being squared there has to be the square root of 2. That's the only thing that when you square it, you get a 2. So your a is actually root 2, which is what they write out in red to the side of example 1b. And then, right, your x squared is not just x squared. It's written as 9x squared, right? But that doesn't mean that 9x is your, like, u, right? Because it's not 9x quantity squared, right? You have to rewrite it as some quantity in its entirety being squared. What quantity in its entirety being squared is equivalent to 9 times x squared? Well, that would be 3x quantity together squared. So that your u is 3x. Right, they write that out in red. Your u is 3x, so the derivative of your u is 3, right? So when your u is not equal to x, you have to have your u prime there so that we're undoing chain rule. So your u prime is 3, so they need a 3 in the numerator. They write the 3 in the numerator. To offset the 3, they multiply on the outside by 1/3. 3 times 1/3 is 1, so they didn't change the value of that thing. So now they can apply their formula. The 1/3 just carries straight down. That has nothing to do with the actual formula of arctan. That's just an extra thing plopped onto the beginning because you have that extra 1/3. Okay, and then again for everything except for arc sine, you have that 1 over a out front. The a is root 2, so 1 over root 2. You know, if you want to be kind of nicer. I don't know, I like rationalizing denominators. I don't know why the book wouldn't do that. Not a huge deal, but it is nicer to do that. So you could rationalize that there. You could make that, let's see, that'd be root 2 over 2 all divided by 3. So like root 2 over 6. Okay, so that's the 1/3 times the 1 over a times arctan of, and again, so the x over a in our arctan formula, x is only x if u equals x. If there's something, right, just like our green boxes back on this screen. If our green boxes say something other than x, then where you see x in our formula, you plug in whatever that whole thing that's in the box with the x. So you plug in the 3x in place of x divided by a is root 2. Again, you could rationalize the denominator. all plus c. Again, hopefully you can help each other if a couple people are stuck or someone's stuck. C, same idea. Notice, and again, the other thing I was going to say on this screen, I think we pointed this out before when we did derivatives. Let's see what I want to use. So, if I can use a different color of, purple. Use a purple highlighter. Okay, notice here that this x and this x squared are together when you see the arcsecant formula. And this x, or this x squared term, that's the one being subtracted in the arc sign, right? Whereas the x is not the one being subtracted, it's the a that's being subtracted in the arcsecant formula. That's really important, okay? So when we look at example 1c, we see that we have an x outside the square root, and then we have our like x squared-ish thing as our first term. That's our positive term under the square root. So that's just screaming arcsecant. Again, we have to rewrite. Yeah, okay, this one's a little bit, I might actually write this one down because the book kind of just breezes its way over it. So this is example 1, part C. These are tricky. I like them, but I completely admit that they are quite tricky. So 4x squared minus 9 dx. Right, the dx they put up in the numerator. That means exactly the same thing. Don't let it freak you out. If you want to rewrite it like this with the 1 up top, it's fine. Okay, so first of all, I'm going to rewrite this like this. I know that this 4x squared thing has got to be written as one single quantity squared. And what is that quantity? It's got to be 2x squared, right? And the 9, that's not going to fly. We have to write it as a squared. So I'm writing this as 3 squared, like that. Dx like this. All right, so this is a 3. So this has to be my u. This has to be, right, 3. Has to be my a. Now notice we have two things going on here. If our u is equal to 2x, fine. Our du dx must be 2. What does that mean? That means we need we need this du dx up here in the numerator, right? So I need this to be multiplied by 2. I need this to be multiplied by 2. Now normally I would immediately go and multiply outside by 1/2. Normally. But hold your horses. Hold this thought. We still need to multiply this whole thing by 2. Because here's where like crazy things happen in this arcsecant thing anytime we use chain rule. It just so happens that it really is always going to work out this way. So another problem we have, so we had the problem that we needed du dx up there because we're undoing chain rule. But we also have the problem, you may not realize it, but this is supposed to be our u. This has to also be u, right? So this must also be equal to u, which is equal to 2x, right? But right now it's just an x. We have to make that a 2x. And we had to make the top a 2x. I mean, we'd make the top a 2 for a different reason, because the derivative of 2x is 2. So remember that whole idea when we just multiplied by the top by 2 and he said, okay, we still owe this equation a times 1/2. Well, just so happens we need this 2 next to this x in the bottom. So if I put this 2 in here, right? So what I've changed about this is that I needed to multiply by 2 on top and a 2 on the bottom, right? And so 2 divided by 2 equals 1. So we just multiplied by 1 actually. So they actually like balance each other out. Great. Okay, so now we apply the arcsecant formula. So 1 over a outside. A is 3. Again, a is 3, not 9. 1 over 3. Arcsecant. Remember, this is the weird one. We have the... we're about to run into this, aren't we? What if I can move this? Can I do my fancy lasso thingy? Whee! Then I move it. Yeah. Okay. Here we go. Okay, so 1 over a, arcsecant of, this is where we do this fancy absolute value thing, and inside the absolute value we need not just an x, because our u is not just x, we need our 2x. So absolute value of 2x over a, our a is 3, all plus c, right? And like the book doesn't put a giant parentheses around the absolute value of 2x over 3, so don't have to. I don't know, it just seems to be clear what's all in the argument there to me. All right. Moving on. Example 2. All right. Again, now they're just going to make your life more and more difficult, essentially. Essentially, if you don't like the kind of problems when Prof 9 starts saying, oh, this is so fun, and you're like, oh no, that means bad things are coming. I hate to break it to you, but that's pretty much the whole rest of this section is just kind of stepping down into the different, I don't know, I guess you could call it stepping up into the different levels of the heavens, or stepping down into the different layers of, Dante's Inferno or something. Okay, so example 2, we're throwing some e's in here. Hold on to your hats, folks. Okay. And whatever they put this, I'm gonna just put a 1 up here. E, it's square root e to the 2x, and that 2x is all in the numerator. I mean, you know what I mean, the thing in the up thing, the exponent. E to the 2x minus 1. Nope, I did not want that. Okay, dx. This is fun. Oh, this is... Ooh, all right. This is fun. All right. And it looks like annoying, but it's like harder than annoying. I'm sorry, that kind of makes me happy for some reason. It's fun. Okay. So now u is not what you think it is. Like, not what it would normally be if we weren't talking about inverse trig stuff, probably. I don't know, like normally if you saw something like, I don't know, if I saw something like this, at first I'd be kind of thinking, oh, maybe my inside function, because remember, you're going to be given these out of context. In fact, I think I wrote on your notes the next test or half test or quiz or whatever it is, I'm sorry, I forget, is, I think I said like literally like 10 integrals. again, it's kind of like my favorite assessment because it's just so straightforward. You know, sometimes you have like conceptual questions or like word problems. This one's literally just, I'm telling you now, there's 10 integrals. One that's kind of integral, kind of not integral, but it has integral in it. Anyways, it's just like 10, boom, 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 integrate, 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 more or less. That's it. No like word problems, just straight up do the integral. Yeah, so that's fun. But let's say one of your 10 is something like this. So you're not going to know that it's going to be in our trig something, you know, they're not going to like warn you. Right? Because if I was looking at this, I might be thinking, maybe my inside function's e to the 2x minus 1. If that were true, the derivative of e to the 2x minus 1 would be 2 times e to the 2x. Well, we don't have a separate occurrence of 2e to the 2x anywhere. So that just can't happen. If we got really confused and tried to just make our inside function 2x and said the derivative of that's 2, well, that's well and good. We can come up with our own 2, but what do we do with a minus 1? Yeah, so we would be stuck. So what we're going to have to do, and even this, again, I will warn you, this one's pretty tricky. This one's pretty tricky. So we have to kind of assume it's some kind of inverse trig thing, since it's not one of the usual suspects, which is a movie that is like my husband's favorite movie. I don't know if any of you have watched that movie. Instead of thinking of it as e to the 2x, think of it as e to the x quantity squared. Okay. Even in that, you're going to have to trust me. Again, this is why I love doing this teaching in person. Because then my next question would be, okay, even if I view this as e to the x quantity squared minus 1 and say, okay, we can call the 1 is equal to 1 squared, sure. My next question to you would be, okay, but why is the answer not straightforward from here? Why should this cause you to scratch your hypothetical beard a little bit in terms of trying to fit this into an inverse trig formula? Well, hopefully your answer would be something along the lines of, well, prof, you see the expression that has the x that's being squared is listed first under the square root. It's like the positive thing. And then you're subtracting a squared. That usually only happens when you have like an arcsecant thing going on, but then you additionally have whatever your u is outside the square root, which we do not have. So I am confused. So you should be a little confused, right? So if this whole thing had just been like the 1 squared minus the e to the x quantity squared, that would at least look better. Granted, if it was like that, it would actually be unsolvable because then your u would be e to the x, your u prime would be e to the x, so you need another e to the x, which you do not have. Anyway, this is fun. Okay. So you're just going to have to kind of like trust the process that somehow something doable is going to pop out here. So let's see what happens if we just kind of trust the process and we say, I think it's going to be some kind of arc trig. We know that's got to be our u. So our u has got to equal e to the x. So our du dx is also e to the x. Okay, so then your next question to me should be, well, okay, so we need an e to the x in the numerator. But we can't multiply by the reciprocal of e to the x outside the integral, prof. You told us that we can't put anything, any expression with an x outside the integral. So what gives? If you remember our last problem, remember kind of like the miracle of what happened last time, though it was a little bit less obvious because it was just a bunch of 2's. Remember how we had like 2 separate problems and they ended up kind of like helping each other out here, like when we had Here the problem where we needed the du dx is 2, so we needed that 2 up there, but we also needed the bottom needed to be a u here, so we needed a 2x here, so we needed that 2. So we needed that 2 up there, that 2 down there. They actually ended up canceling. Now those are just constants, so that was kind of like, meh, child's play. Down here, this is not child's play anymore. We're not kidding around, because instead of needing an extra times 2, we need an extra times e to the x, which we can only do inside the integral, so we're desperate. Please, 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 give us a way to solve our problem. So we need an e to the x. Let me start this. So we need this e to the x up here. We need this e to the x. Oh please, let us do that. It's the only way we can survive this problem, because that's u prime. But what we also need, and again, related to what your hypothetical, great hesitation was expressed by hypothetical student that I made up, is that this looks like an arcsecant problem, and we need, right, we would need our u, just like we have the u squared here, we need the u outside the integral, outside the, not the integral, outside the square root sign. So we need that integral here, but to fit arcsecant, we also need this here, right? To fit, so this is to fit the arcsecant form, right? So we need e to the x there, in addition to having what we had here, e to the x quantity squared minus our a squared dx. Well, look at that. So again, we had two problems. We needed our du dx up top, which was e to the x, and we also needed an extra x, or the book kind of calls it u, here, right? We needed this here in order to fit the form for arcsecant, and it had to be arcsecant because this expression in terms of x squared was the one in the front, the positive expression under the square root. So we couldn't have made it an arc sine even if we wanted to. But actually those two things, needing essentially the u expression up top, or the du dx expression up top, and needing the u expression outside the square root in the denominator, and it just so happens, right, that e to the x is both u and u prime here, because it's e to the x. So what is the answer? All right, so we have an arcsecant problem. So 1 over a, our a is just 1, so that's going to be uneventful, times arcsecant absolute value of the u part, so that's e to the x, over a is 1 plus c, like that. So this is just equal to arcsecant e to the x plus c. So if you want to see it all together, it's like that. Oh, that's example 1 and 2, just kidding. Just example 2 is like that. Tricky, 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 tricky. That one's difficult. Again, these involve critical thinking. These involve kind of taking intellectual risks and just hoping and relying on your mathematical intuition and integrity. This sounds dramatic, but your ability to just adhere to the rules of math, try things, see if somehow when you kind of start going in the puzzle one way, it'll just kind of work itself out. Okay, I'm going to skip example 3 for now. We're coming back for sure. Example 3 is a certain form of trickiness. Actually, Yeah, whatever. Okay. Because I wrote in my notes that I would come back to it. So I'm going to go ahead and do examples 4 and 5. And if you're following along in your book, you'll see the red heading for examples 4 and 5 is completing the square. Wow. See, again, I don't know. I know I'm a math nerd. That's why I'm teach calculus, since it's like my favorite thing to teach, but it's just the gift that keeps giving. We keep having things come up, like we had long polynomial division come up in the last section. We have completing the square come up this time, just like all these like random things that, you know, you learned from me and from other people earlier in your high school career. And like they're actually important, and they like help you solve these like cool little math puzzles. Okay. So again, I'm skipping example 3 for a little bit. I'll come back to it. Example 4. I'm not going to really warn you on how to do this. We're just going to figure it out ourselves as we go. Example 4, we're trying to find, oh, I wanted to zoom back in a little bit. Sorry, if I don't zoom in, then it's going to mess up the thickness of these lines. Example 4. Okay, and again, keep in mind the context of these. And I'm just going to go ahead and write the dx up top because I think it freaks some people out, and sometimes it's good to be freaked out. Better to freak you out now than on the test. X squared minus 4x plus 7. Again, the elegance of these problems, like this problem, you just look at it and it seems so simple. And again, like pretend like we had no context for this problem. Pretend like you're, taking a test in April, or you're taking the AP test or something, and you have to do this integral. And it just looks like you're trying to find the antiderivative of this, like, 1 over this polynomial thing. And it's just so simple. But then, like, what the actual answer ends up being. Okay, anyways, I gotta stop talking. Just keep working. But again, you see this, and again, let's pretend like we don't know where this is going. If you see this completely out of context, here's the things you should be thinking about. Here's the things I would be thinking about. I see this polynomial. First of all, I think, what if something like, I don't know, could I factor it? Well, there are two things that multiply to get 7, add to get -4. No, at least not like whole numbers. Okay. What if we chose our u to just be the entire denominator? Okay, but then our u prime would be 2x minus 4. Is there any way we could get 2x minus 4 from a numerator that's literally just a 1? No, we can't. I mean, if it was just a -4 or -4, we could pull that off. If we got a 2x minus 4, we can't just pull that from thin air. No, so that's hopeless. So then you just have to know that this arc trig stuff sometimes just comes out of nowhere and is just something that it just is. Like, there's sometimes problems that don't look weird at all, don't look weird enough to think that you'd be using inverse trig. You have to use inverse trig. Well, prof, how would we use inverse trig here? Okay, well, could you use arcsine? Could you use arcsecant? No and no, or hopefully your answer is why? Because there's no square root in the denominator, right? And there's no like fancy way to like put a square root in the denominator. So you can't, right? Those aren't going to apply. So just like I said, arctan is going to be used way more often than arcsine and arcsecant. Okay, so this is going to be an arctan problem. Okay, how could it be an arctan problem? Well, we need to force it to be, again, the order doesn't really matter. We need to force it to be some expression. I'm going to just write this in for now, and then we're going to come back to this. Right? Some This is going to be some kind of u. This is going to be some kind of a. And this is going to be u prime, or, du dx. Right? And then it's going to equal some, it's going to be equal some arctan tan thing, right? Blah, 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 plus c, blah, blah, blah. All right, that's where we're going with this. So, how do we know what's going to be our u, what's going to be our a? Well, again, the red heading gave it away. Completing the square. Whew. It's been a while. What do I mean by completing the square here? Well, we got to work with what we're given. So we're given, right? Obviously, this whole bottom is not equal to a binomial squared, but we can make part of it equal to a binomial squared. And we have to use the x squared and the minus 4x that we're given. So we're going to use this to complete the square and rewrite this as a binomial squared. Complete the square with this. To rewrite this as a binomial squared, right? So this is actually going to be like x plus or minus some number. Okay, I write minus because it's x squared minus 4x. In this case, it could be plus. All right, so we're getting down here. Okay, dx. All right, how do you complete the square? Remember, take half the middle term, square it. Okay, so what we really need here, x squared minus 4x, again, to complete the square. You take the middle term, take half of it and square it. So negative 2 squared is positive 4. So we need a positive 4 here, right? But we can't change the value of the denominator. We can only like rewrite it in a fancy way. So we can make this plus 4, which is what we need. So I'm going to group those together, but then we're still left with an extra, right? We need this to be a 7, so we make this plus 3, so that, right, this together is equal to 7. You see that? Okay. So when we rewrite this whole thing, it's going to be dx up top. Again, we're writing this as a binomial squared here. That's the point of completing the square. When you write the binomial squared, you take half the middle term to know what goes in the binomial. So x minus 2 squared is what that whole trinomial is equal to, right? That is that. Plus, now be careful because now we have to write this as a squared. We can't just write it as a number. So we need to write this as an a squared, right? So that means this is our u, this is our a, right? Do we need something up top? What is our du, dx? It's just 1. So we're good to go. This is already a 1. It's already a 1. Okay, so now we can write the answer. This is an arctan problem. Arctan starts with 1 over a. Arctan. This is just u over a. U is x minus 2 over a plus c. That's it. Not too bad. But kind of crazy at the same time. All right, we're going to do example 5. Which again looks a little tricky. Okay, again, if I zoom out to show you the whole problem in case you need to like pause it. That's example 4. Okay, example 5. Okay, example 5. Find, again, they're just asking this in a different way. Find, to remind you of the big picture here, the area of the region bound by the graph of f of x equals 1 over root 3x minus x squared. The x-axis and the lines x equals, this is kind of strange, x equals 3/2 and x equals 9/4. 9/4. Kind of strange. If you look at the in the textbook, it has a little picture, but basically this graph, I guess, at least this little part of it kind of looks like this. That's kind of lopsided, but and then this is like here into like here. It's like wanting you to find that area. All right. Just it's saying just like don't lose sight of the fact that, remember, anytime you do a definite integral of a function between 2 points, you're finding the area under the curve between those 2 x points. All right, so really they're just saying find integral from 3/2 to 9/4. Oh, that doesn't look good. Oops. To 9/4. Now this needs to be moved down a little bit. Here we go. Okay. Of 1 over, oh, this is gonna need some work. Let me save some room. Dx. Whatever, I guess I'll just have to write it like this and I'll rewrite it later. Okay, so that's what they're asking for. That's a 4. Right, that's what they're asking for. Nothing fancy. Now again, this should cause you pause in your brain. Again, if you're asked completely out of context about this, probably your first thought's not necessarily going to be arc trig. So it's not normally anyone's first guess at how to solve a problem. First guess would probably be, oh, what if our u is 3x minus x squared? If so, our u prime would be 3 minus 2x. Where are we getting 3 minus 2x from? I have no idea. That's hopeless. Can't do that. Right, so then hopefully we're starting to freak out enough to go, well, maybe, I don't know, maybe some kind of inverse trig. Right, well, what kind of inverse trig? Well, can't be arctan. We got to cross that off, unfortunately. So we got a square root. And sometimes you can't tell until you really get into the meat of the problem whether it's going to end up being an arc sine or end up being an arc secant. This one's kind of harder to guess at with you guys being noobs because one of the x terms is positive and there's another x term and it's negative, so it's kind of like, what's going on? Well, let's think about completing the square. Okay. You go to complete the square here. It's really going to go based on the sign of the x squared term. If the x squared term was positive, right, kind of like up here, I mean, we did tan, so most things are positive up here, right? When the x squared term was positive, that means, right, this x squared term was positive. So this binomial squared got to be out front. It was nice and positive. Granted, this was also a plus because it was arctan. But here, this x squared is negative. So when we actually go to complete the square here, what's going to happen? There might be a lot going on, so I'm going to just kind of extend this out. Dx is out here somewhere. I don't know how long it's going to go out for. Okay. So we're going to have to subtract, and then our x squared term is going to be in here. In fact, right now we have, and this 3x is going to have to be in there with the x squared term. So we're actually going to have to make that a negative negative, like subtracting a negative. So that's equivalent to positive 3x. So since it has to go in here in this parentheses with the x squared, we're going to make this minus 3x. You see that? Right. That's not what I was meaning to do. Right. We're subtracting the negative. So that's because it's equal to a positive right there. So that what our goal is going to be to have our a squared here and this to be our u squared. Okay. And then if there's any u prime, it would have to go up here. U prime. Kind of made that sideways. I didn't want it to look like u to the first power. Okay, so we have to complete the square again. So completing the square. Complete the square, right, for this thing. So we take half of it, square it. It's going to end up being 9/4, looks like. 9/4. Okay, so we need a 9/4 here. You're going to have to be real careful. So plus 9/4. Right, I can't just come in and just add a 9/4. In fact, what I really did, again, think back to when we completed the square back in 10th grade, when it was like transforming to vertex form, that kind of deal. I didn't actually add 9/4. I actually subtracted 9/4 here. So if I subtracted 9/4 there, that means I need to add 9/4 here, right? So I need to add 9/4 here, right? And we're all doing this all inside the square root so that it's, you know, canceling out within the square root, right? Plus 9/4 in the square root, minus 9/4 in the square root. So that would all cancel out. Okay. So let's go ahead and rewrite this. So 9/4, 3/2. That's annoying. All right, so we have just a 1 up top for now. Square root, again, we're going to write this as a squared. 9/4 written as something squared is 3/2 squared. 3/2 squared. Minus, we want a binomial squared here. Our binomial is x minus 3/2 because half of the middle term squared dx. So that's just rewriting what we just had. And now let's identify what a and u are, see if there's any u prime to be dealt with, right? This is an arc sine problem, so we don't need the extra u outside the square root. So this is our a. It's a 3. Right, so a equals 3/2. Our u is here. U equals 3 you know what I mean. x minus 3 halves. So our u prime, our du dx is 1. So that's already a 1. That's fine, right? So since we're not formally going all the way into u's, we can keep our bounds as x bounds, okay? So now we make this fit. Now we make this fit the arcsine form. Arcsine has no 1 over a out front, so we just jump right into arcsine. U over a. So u is our x minus 3 halves. A is 3 halves. Now we normally do a plus c, but we don't have a plus c here. We have our bounds to plug in. 3 halves up to 9 fourths. Okay, it's kind of nasty. No, okay, it ends up being not so bad. Well, when we plug in 9 fourths, so, ooh, sorry, my baby is waking up and moving and grooving because mommy just ate. Arcsine 9 fourths minus 3 halves is the same as 9 fourths minus 6 fourths. 9 fourths minus 6 fourths. So 9 fourths minus 6 fourths over 3 halves. All that. And the next one where we plug in x is 3 halves, that's easier. Minus arcsine 3 halves minus 3 halves over, I don't really care, but sure, it's also 3 halves. Right, so this is going to be a 0. So this is just a slight little annoyance of trying to work this out at the end. So 3 fourths over 3 halves. 3 fourths over 3 halves. Little complex fraction-y puzzle for you. Again, it's like the little puzzle box. Minus arcsine of 0. In this case, the 3's like cancel each other to 1. 1 fourth minus 1 half is the same as 1 half, or 2 fourths, which is 1 half. So arc sine 1 half minus arc sine 0. We always do this in radians. Okay, so write your answer in radians, and we're going to just choose like the lowest radian thingy, you know, like kind of closest to 0, right? So arc sine of 1 half, again, for you crazy people out there who still don't understand what arc sine is, this is saying sine of what angle gives you 1 half. And then arc sine of 0 is sine of what angle gives you 0. So sine of, right, 1 half is the small thing. So we're talking about the smallest thing here. So that would be pi over 6. Yep. Okay, so this is pi over 6, right? When sine of theta equals 0, well, the y value is 0, that's just here. That's just 0. 0 radians, 0 degrees. So all things equal to pi over 6. Which is pretty crazy, considering where we came from, that we were just asked the area under this graph up here that looks like it has nothing to do with trigonometry between those two things is actually a multiple of pi? You kidding me? I don't know. Don't you think that's kind of fascinating? I kind of think it is. Okay. That's completing the square. I think I'm going to cut this video off, especially because it's over an hour, and I'm going to come back. The next video I'm going to do is going to be some tricky problems done together, example 3, and homework problems. Think 19 and 41. And then either as part of that video or as the final video for this section, I will talk about examples 6, 7, and homework problems 55, 56, 57, 59. That has to do with like wrapping everything up, and those are kind of fun little puzzles where you change one little thing about the integrand and it changes everything. In some cases, you will not even be able to do the integral based on the knowledge that you have. Okay. Well, hope you're all doing well, as usual, and hope you still feel like you're learning and somewhat enjoying calculus in my absence. You can keep me in your prayers, I'm sure, as I am probably sleep deprived, with a little bit of cabin fever. Yep. And yep, hope you're doing well. Godspeed. God bless. Goodbye.